In question 1, we've got the histogram showing the distances in kilometers that 270 people travel to work. And given that 60 of these people travel between 10 and 20 kilometers to work, we need to estimate the number of people that travel between 22 and 45 kilometers. Well, the first thing to do here is draw a table of frequencies. We've got the classes here. So I've got distance, I've got frequency, class width, and frequency density. My classes are 0 to 5, 5 to 10, 10 to 20, 20 to 30, and 30 to 60. I can easily derive the class width for each of these classes. So for 0 to 5, it's 5, 5 to 10 is 5, 10 to 20 is 10, then 10, and then 30. And we have been given that 60 people are between 10 and 20 kilometers. So we've got the frequency here. I'll write this down. The frequency is 60. And we know that the frequency density is equal to the frequency over the class width. So 60 divided by 10 is 6. And this will help me scale the vertical axis, the frequency density axis. So 10 to 20 this here is 6. So I can proceed with scaling the rest of the axis. So this is here 2, this is 4, and we've got 8, we've got 10, 12, 14, 16, 18, and 20. This will help me read off the frequency density for each of the remaining classes. So between 0 and 5, the frequency density is 20. Then it goes down to 14, then it's the 6 we have already found, then it's 2, and then it's 0.8. And knowing that if I multiply the class width by the frequency density, I'm going to get the frequency. I can proceed with the rest of the rows on my table to find the missing frequencies here. So 5 times 20 is 100. Then we've got 5 times 14, which is 70. Then it's 10 times 2, which is 20. And then 30 times 0.8, which is 24. Well, we've been asked to estimate how many people travel between 22 and 45 kilometers. So 22 to 45 kilometers. This means that we will be looking at surely the class that spans between 20 and 30, and then the 30 to 60. Now 22 up to 30, it's 8 out of 10 of this class. So 8 over 10 of the total frequency between 20 and 30, which is 20, plus the 45, which is exactly halfway through the 30 to 60. So we've got 15 over 30 times the 24 people we've got in the 30 to 60 class. Well, if we plug this on the calculator, we get an answer of 28 people, which is our estimate for the number of people who travel between 22 and 45 kilometers. In part B, we need to find the median distance traveled to work by these 274 people. Here's the frequency table we had from part A. I will add an extra column at the end for cumulative frequencies, so I'm adding up frequencies. So I start with 100, I'm adding 70, I'm to 170, then another 60, I'm at 230, another 20, we're at 250, and finally 274, which is the total frequency. Now to find the median is the middle observation, so I'll be doing n over 2, which is 274 divided by 2, which is 137. And looking at our frequency table, the 137th value is between 5 and 10. So I quickly draw this diagram here. I want to interpolate between 5 and 10. So 5 is my start point, 10 is my end point. I'm trying to estimate the median, so I'll call that M. I'm going to put the frequencies below. So the last frequency not to be included is the 100th observation, and the last one to be included is the 170th observation, and we need to interpolate for the 137th observation. So I'll be doing the small gap over the small gap to be equal to the big gap over the big gap. So we're looking at M minus 5 over 137 minus 100 being equal to 10 minus 5 over 170 minus 100. This leads to M minus 5 over 37 is equal to 1 over 14. I will cross multiply to get M minus 5 is equal to 37 over 14, which leads to M being equal to 7.64 kilometers. And in part C, we need to find the mean distance traveled to work by these 274 people. Here are the classes and the corresponding frequencies. I'll be adding an extra column for the midpoint, which I will call X. Well, the midpoint of the 0 to 5 class is 2.5. I'm doing 0 plus 5 over 2. Then it's 7.5. Then it's 15. Then it's 25. And then it's 45. And we know that the mean X bar will be the sigma Fx over the sigma F. So we're looking at 100 times 2.5 plus 70 times 7.5 plus 60 times 15 plus 20 times 25 plus 24 times 45, and all of it divided by the total frequency, which we know is 274. Well, this gives an answer of 11.9 kilometers. In question 2, we've got data on the weight W grams and the tail length T centimeters of 15 miles. We've got some summary statistics here, and we need to calculate STW and SWW. Well, STW is defined to be the sigma TW minus the sigma T times the sigma W over N. This is equal to 2,304.53 minus the sigma T, which is 114.8, times the sigma W, which is 297.8, divided by the number of observations, which is 15. This gives an answer of 25.4. And for SWW, this is equal to sigma W squared minus the square of sigma W divided by N, which is equal to 6,089.12 minus the 297.8 squared divided by 15. This is giving an answer of 177. In part B, we need to calculate the value of the product moment correlation coefficient between W and T, and we know that the product moment correlation coefficient R is given by STW over the square root of STT times SWW, where we just found STW to be 25.4 ... I'm using full accuracy here, over the square root of 5.3173, which is the STT given by the question, times 177. Which is the exact value of the SWW. This gives an answer of 0.827. And then in part C, we need to show that the equation of the regression line of W on T can be written as W is minus 16.7 plus 4.77T. Well, we know that the equation of the regression line is W is equal to A plus BT. B is the gradient, and this is found by doing SWT over STT. So in our case, it's 25.4 over the 5.3173. This gives an answer of 4.77686 ... And for A, we know that W bar is equal to A plus B times T bar. So we're looking at 297.8 over 15 being equal to A plus the value of B of 4.77686 ... times T bar, which is 114.8 over 15. Now this leads to 19.853 ... being equal to A plus 36.5589 ... and therefore A turns out to be minus 16.70557 ... So my final answer is that the equation of the regression line of W on T is W is equal to minus 16.7 plus 4.77T as required. In part D, we're asked to give an interpretation of the gradient of the regression line. We know that the gradient represents the increase in y for every unit increase in x. So in our case, the gradient was found to be 4.77. Our x is t, it's the tail length in centimeters, and our response variable, our y, is w, which is the weight. So we can easily conclude that for every extra centimeter in tail length, the weight is increasing by 4.77 grams. In part E, we need to explain why it would be inappropriate to use the regression line in part C to estimate the weight of a mouse with a tail length of 2 centimeters. Well, I will start by trying to estimate W when T is 2. So we say that when T is equal to 2, then W is minus 16.7 plus 4.77 times 2, which gives an answer of minus 7.16, which is obviously negative, which is certainly impossible. So since the weight cannot be negative, it would be inappropriate to use the regression line. Now Sean decided to code the data using x is t minus 6 and y is w over 2 minus 5, and we need to write down the value of the product moment correlation coefficient between x and y. Well, we know that the PMCC is not affected by linear coding and therefore R is 0.827. And finally, in part G, we need to write down an equation of the regression line of y on x. We do not need to simplify our equation, so we simply need to substitute and get rid of the t and the w, replace this with x and y. We've got that x is equal to t minus 6 and therefore x plus 6 is equal to t. And we've got that y is equal to w over 2 minus 5. I will multiply throughout by 2 to get 2y is equal to w minus 10. And therefore 2y plus 10 is equal to w. Now we have already established that w is minus 16.7 plus 4.77t. So I will be replacing w with 2y plus 10. So we're looking at 2y plus 10 is equal to minus 16.7 plus 4.77 times t, which is x plus 6. And that's the final answer for part G. In question 3, Jim has recorded the length L millimeters of 81 salmon. The date has been coded using x is L minus 600. We've got the following summary statistics provided to us, and we need to find the mean length of these salmon. Well, I will start by finding the coded mean. So x bar is sigma x over n. This is equal to 3,711 over 81. And I will proceed in finding L bar, which is the actual mean length of the salmon. Well, we know that if x is L minus 600, then the mean is affected in exactly the same way. So x bar is L bar minus 600. I will replace x bar with 3,711 over 81, which is equal to L bar minus 600. And solving for L bar, we find that this is equal to 646. We are then asked to find the variance of the lengths of this salmon. I will start by finding the coded variance sigma squared x, which is equal to sigma x squared over n minus the sigma x over n all squared, which is equal to 475,181 divided by 81 minus the 3,711 over 81 and all squared. This gives an answer of 3,767, and we know that the variance, the spread, is not affected by adding or subtracting a constant, a number. So this means that sigma squared x is equal to sigma squared L, and therefore we conclude that sigma squared L, the variance of the lengths, is equal to 3,767. Now the weight W grams of each of these 81 salmon is recorded to the nearest gram, and the results are illustrated in the box plot shown here. We need to find the maximum number of salmon that have weights in the interval of W being strictly greater than 4,600 but less than or equal to 7,700. Well, the 4,600 is exactly in the middle, it's the median, and the 7,700 is the maximum value observed. Well, we know that half of the observations are above the median and half of them are below. I need to be strictly greater than the median. So if I do 81 divided by 2, I get 40.5. Obviously, I cannot have 41 observations on the right-hand side of the median because that would mean I have 41 observations on the left-hand side, and therefore this violates the fact that the total is 81 because this gives me 82. So we conclude that we've got 40 salmons which are greater than 4,600 but less than or equal to 7,700. I've got 40 on the right-hand side, 40 on the left-hand side, and the last one is exactly the median, so everything adds up to 81. We're then given a rule for identifying an outlier. It's anything that lies 1.5 times the interquartile range above the upper quartile, or more than 1.5 times the interquartile range below the lower quartile, and we need to show that there are no outliers. Well, let's look at our box plot. We can easily see from the box plot that the lower quartile Q1 is equal to 3,800. Our upper quartile Q3 is 5,400, and therefore the interquartile range defined to be Q3 minus Q1 is equal to 5,400 minus 3,800, which gives an answer of 1,600, and therefore we can proceed in finding the limits for outliers. So I will calculate Q1 minus 1.5 times the interquartile range, which is equal to 3,800 minus 1.5 times the 1,600. This gives an answer of 1,400, and Q3 plus 1.5 times the interquartile range is equal to 5,400 plus 1.5 times the 1,600, which gives an answer of 7,800. Well, looking at the box plot, the minimum we have seen is 1,600 and the maximum we have seen is 7,700. Therefore, we can easily conclude that since 1,400 is less than the 1,600, as well as the 7,700 being less than the 7,800, so the minimum is greater than the limit on the left-hand side and the maximum is less than the limit on the right-hand side, and therefore we conclude that we've got no outliers. In question 4, we've got a bag containing a large number of colored counters labeled A, B, or C. Now we've got 30% of them being labeled A, 45% B, and the rest are labeled C. It is additionally known that 2% of the counters labeled A are red, 4% of those labeled B are red, and 6% of those labeled C are red. And we are choosing a counter at random, and we need to complete the tree diagram given here. So we know that the probability of picking B is simply 0.45, and the probability of picking C is 0.25. Remember that these three probabilities need to add up to 1, because when I draw a counter, surely one of them will be A, B, or C. Now the probability that it's red, given that I picked A, is 0.02, so the probability it's not red is 0.98. Now the probability it's red, given that it was B, is 0.04, so the probability it's not red is 0.96. The probability it's red, given that it was C, is 0.06, and the probability it's not red is 0.94, which completes the tree diagram. In part B, we need to calculate the probability that the counter is labeled A and is not red. So A and not red means I need to multiply 0.3 with 0.98. So if we do 0.3 times 0.98, we get an answer of 0.294. In part C, we need to calculate the probability that the counter is red. So looking at the tree diagram once more, we're going to be at the A and red, or B and red, or C and red. So I will be adding up the three probabilities, 1, 2, 3. So I will simply be doing 0.3 times 0.02, that's the first probability, plus 0.45 times 0.04, that's the second probability, the probability of being B and red, plus 0.25 times 0.06. Well, this gives an answer of 0.039. In part D, we have that given that the counter is red, what's the probability that it is labeled C? So this is an example of conditional probability. We surely know that the counter we've picked is red, so we are here, here, or here. The question is, what's the probability that the counter came from C? What's the probability we are here? So the numerator is going to be the 0.25 times the 0.06, while the denominator will be the event that we know for sure to have happened, the probability of being red, which is the sum of these three probabilities, or simply the answer we obtained in part C. So we're looking at 0.25 times 0.06 is the probability of drawing from C and being red, over 0.039, which is the probability of red, which gives an answer of 5 over 13. In question 5, we've got a discrete random variable y with the following probability function. We need to show that k is 1 over 30. When looking at the function here, we can easily conclude that the random variable can attain the values of 1, 2, 3, 4, 5, or 6. So we strongly suggest you draw up a table to see all the possibilities and all the associated probabilities. So we've got y attaining values of 1, 2, 3, 4, 5, or 6. And let's look at the probabilities of y attaining each of these values. Well, if y is 1, we are looking at 3 minus 1 times k, so we are looking at 2k. If y is 2, we've got 3 minus 2 times k, which is equal to k. If y is 3, then we've got 3 squared minus 8 times k, so it's 9 minus 8, which is 1, so it's again k. Now for 4, we're going to do 4 squared minus 8 times k, which leads to 8k. For 5, 5 squared minus 8 is 17, so we're looking at 17k. And for 6, it's just k. And we know that the sum of the probabilities should be 1. So if we do 2k plus k plus k plus 8k plus 17k plus k, we should get an answer of 1. This leads to 30k is equal to 1, and therefore k is 1 over 30 as required. In part B, we need to find the probability of y being greater than 1 but less than or equal to 4. So let me write this down. 1 less than y less than or equal to 4. This simply means that y could be 2, 3, or 4. So looking at the table of values here, it's k plus 8k. So let me write this down. It's k plus 8k. This gives an answer of 10k, which is 10 times 1 over 30, which simplifies to 1 over 3. In C, we need to find the expectation of y, and we know that for the expectation, we multiply each outcome by the associated probability. So it's going to be 1 times 2k plus 2 times k plus 3 times k plus 4 times 8k plus 5 times 17k plus 6 times k, which leads to 2k plus 2k plus 3k plus 32k plus 85k plus 6k. If we add up all the k's, we get 130k, and we know that k is 1 over 30. So 130 times 1 over 30 gives an answer of 13 over 3. We're then given a new random variable x defined to be 15 minus 2y, and we need to calculate the probability of y being greater than or equal to x. So the first thing to do is substitute the x with the expression we were given, so it's 15 minus 2y. I will solve the inequality within the probability, so it's the probability of 3y being greater than or equal to 15, which is the probability of y being greater than or equal to 5. Well, this simply means that y could be 5 or 6, which means we're looking at 17k. That's the probability of y being 5 plus k, which is the probability of y being 6, which is 18k, which is 18 times 1 over 30, the value of k, which simplifies to 3 over 5. And in part D, we need to calculate the variance of x. Well, I will start by calculating the expectation of y squared, which is each outcome squared times the associated probability. So we're looking at 1 squared times 2k plus 2 squared times k plus 3 squared times k plus 4 squared times 8k plus 5 squared times 17k plus 6 squared times k. This leads to 2k plus 4k plus 9k plus 128k plus 425k plus 36k. So we're looking at a total of 604k, which is 604 times 1 over 30, which gives an answer of 302 over 15. This is the expectation of y squared. Well, we know that the variance of y is given by the expectation of y squared minus the square of the expectation, and we simply have the expectation of y squared being 302 over 15, and the expectation of y being 13 over 3, so I've got 13 over 3 squared, which gives an answer of 61 over 45. Now we know that x is 15 minus 2y, so the variance of x is simply the variance of 15 minus 2y. Well, the 15 is not affecting in any way the variance, the spread of the random variable. However, the negative 2 will come out squared. So we're looking at negative 2 squared times the variance of y. So we're looking at 4 times 61 over 45, which gives an answer of 244 over 45 for the variance of x. In question 6, we've got three events A, B, C. We've got the probability of A being 0.1, the probability of B given A to be 0.3, the probability of A union B to be 0.25, and the probability of C being 0.5. We are additionally told that A and C are mutually exclusive, and we need to find the probability of A union C. Well, first of all, we know that if two events are mutually exclusive, then their intersection is empty, so the probability of A intersection C is 0. Additionally, we know that for any two events, the probability of A union C is the probability of A plus the probability of C minus the probability of A intersection C. So the probability of A is 0.1, the probability of C is 0.5, and the probability of their intersection is 0. So A union C is 0.6. In part B, we need to show that the probability of B is 0.18, and I will start with the fact that the probability of B given A is 0.3. Well, we know that the probability of B given A is the probability of B intersection A over the probability of A. So we're looking at 0.3 is equal to the probability of B intersection A over 0.1, which is the probability of A. And if I cross multiply, I get 0.03 to be the probability of B intersection A. Additionally, we know that the probability of A union B is the probability of A plus the probability of B minus the probability of their intersection. The probability of A union B is 0.25, the probability of A is 0.1, the probability of B is what I'm trying to find, and the probability of A intersection B is 0.03. This leads to 0.25 to be equal to 0.07 plus the probability of B, and therefore the probability of B turns out to be 0.18 as required. We are additionally given that B and C are independent, and we need to draw a Venn diagram to represent the events A, B, and C and the associated probabilities. Well, B and C being independent simply means that the probability of B intersection C is the probability of B times the probability of C, which is 0.18 times 0.5, which gives an answer of 0.09. And therefore we can proceed by drawing a Venn diagram. A and C are disjoint circles because A and C are mutually exclusive events. We have already established that A intersection B is 0.03 and B intersection C here is 0.09. Well, we know that the probability of A is 0.1, so the only A region is 0.07, while the probability of C is 0.5, so the only C region is 0.41. Additionally, we have found that the probability of B is 0.18, so if I deduct the 0.09 and the 0.03, I'm left with 0.06 for the only B region. And if I add everything in A, B, or C together, I need to put a number here that will make the total 1. So if I add these numbers here, I get an answer of 0.66. So I need a 0.34 outside the three circles to ensure that the total probability in my Venn diagram is equal to 1. In question 7, we've got a machine squeezing apples to extract their juice. The volume of juice, capital J milliliters, extracted from a kilogram of apples is modeled through a normal distribution with a mean of mu and a standard deviation of sigma. Now initially mu is 500 and sigma is 25, and we need to use standardization to show that the probability of J being greater than 510 is 0.3446. So there it is, J is the volume, J follows normal 500, 25 squared. So the probability of J being greater than 510, I will start by standardizing. It's the probability of Z greater than 510, and I will deduct the mean of 500, and I will divide by the standard deviation of 25. This leads to the probability of Z being greater than 0.4, which I will write as 1 minus the probability of Z being less than 0.4. And going to the table of values for the normal distribution, for 0.4, we read off the value of 0.6554, which means we're looking at 1 minus 0.6554, which gives an answer of 0.3556 as required. In II, we need to calculate the value of D such that the probability of J being greater than D is 0.9192. So starting with what we are given, the first thing to do is standardize. We've got the probability of Z greater than D minus 500 over 25 is equal to 0.9192. Now for me to use the big table of values, I need to make sure that we're looking in the less than direction. So this will be written as the probability of Z greater than 500 minus D over 25 being equal to 0.9192. And going to the big table of values, looking into the probabilities for 0.9192, we read off the Z score of 1.40, which means that 500 minus D over 25 is equal to 1.40. If we cross multiply, we get 500 minus D being equal to 35, and therefore D turns out to be 465. Now Zen randomly selects 5 bags, each containing 1 kilogram of apples, recording the volume of juice extracted from each bag of apples. We need to calculate the probability that each of these 5 bags will produce less than 510 milliliters of juice, while the probability of J being less than 510 is 1 minus the probability of J being greater than 510, which was the answer to part A. So this is 1 minus 0.3446, which gives an answer of 0.6554. which is the probability of 1 bag giving us a volume of juice of less than 510 milliliters. Remember, we're trying to find the probability of all 5 bags producing less than 510 ml of juice. So this will simply be the 0.6554 raised to the power of 5, because I want all 5 of them, and this is equal to 0.121. Now, following adjustments to the machine, the volume of juice capital R extracted follows a normal distribution with mean 520 and standard deviation K. Additionally, we've got that the probability of R being less than small r is 0.15, and the probability of R being greater than 3R minus 800 is 0.005. And we need to determine the value of R and the value of K. So we now have R following normal 520 K squared. The first piece of information was that the probability of capital R being less than R is 0.15. We will standardize to get the probability of Z less than R minus 520 over K is 0.15. Now the probability of 0.15 can be found in the small table of values, so I need to make sure that I'm looking in the greater than direction. So I will rewrite this as the probability of Z greater than 520 minus R over K being equal to 0.15. And going to the small table of values for 0.15, we read off the Z value of 1.0364, which means that 520 minus R over K is equal to 1.0364. And therefore 520 minus R is 1.0364K, which leads to 520 minus 1.0364K is equal to R. Now the second piece of information was that the probability of capital R being greater than 3R minus 800 is equal to 0.005. Once more, this probability can be found in the small table of values. I'll be using the small table, but first I need to standardize. We're looking at the probability of Z greater than 3R minus 800 minus the 520 over K being equal to 0.005. So in the small table of values, the corresponding z-score is 2.5758, which means that 3r minus 800 minus 520 over k is equal to 2.5758. I will cross multiply and I will simplify the left-hand side, leading to 3r minus 1320 is equal to 2.5758k. This means that 3r is equal to 1320 plus 2.5758k. So I'll be using simultaneous equations to determine the values of r and k. The first thing to do is take this equation here and multiply everything by 3 to get 1560 minus 3.1092k is equal to 3r, and therefore I can equate these two to determine the value of k. So we are looking at 1560 minus 3.1092k being equal to 1320 plus 2.5758k. So we've got 240 being equal to 5.685k, and if I divide both sides by 5.685, we get 42.21635 ... for the value of k. Now to get the value of r, I will substitute into 520 minus 1.0364k. So this means that r is equal to 520 minus 1.0364 times 42.21635 ... So we get that r is equal to 476.2469 ... And therefore we conclude that k is 42.2 and r is 476, both correct to three significant figures.